T4, please.
Okay, first of all, let me thank the organizer to have invited me to be here. I'm very happy for this edition of IGST. Let me also give a quick announcement. I took the umbrella of someone else yesterday, and I left it here, so you're free to claim it back. My talk will be indeed about massive and massless dressing factors, and is based on working collaboration with Sergei Frolov and Alessandro Sfondrini. The past years, Alessandro Sfondrini gave a similar talk actually in São Paulo, and I think Bogdan gave a similar talk in IDD at that time. And now we are here together, so we can actually fight for. But what it is about? It's about string theory in this background, AdS3 S3 T4, in the presence of mixed flux. And this is a family of classicable integrable model, which is defined by two free parameters, which is the amount of Nevers-Warth flux and Ramon flux. And I will label this by these two parameters. K is an integer, which can be 0, 1, and so on and so forth, while H, which is the amount of Ramon flux, is bigger or equal to 0. And some is known. For example, if you take H equal to 0, exactly equal to 0, then the worksheet strings is defined by a Vezzomino-Witten model on this worksheet. And this can be studied by conformal field theory method. And also in the case in which you have a minimal amount, for example, of NSNX flux, and you eventually deform by introducing some small amount of Ramon flux around this background, the dual conformal field theory, there is a proposal which comes from Eberhard, Gaberdi, and Gopakumar, and people studied on the CFT side what this should correspond to. But as we turn on a big amount of H, so we have a big amount of Ramon flux, this conformal field theory method kind of fall down. And we believe the most useful thing is to study the theory by integrability. And a lot of progress has been done in the past year in the case in which you have exactly K equal to 0, so no NSNS flux, but just Ramon. And there have been different groups that have studied these theories either from the worksheet perspective and tried to derive what are the thermodynamic Bethe ansatz for the pure Ramon case. In particular, Frolov and Sfondrini derived these equations, and there was also some studied, numerical studied. Many people in this audience instead derived directly some quantum spectral curve. So there is still some gap between thermodynamic Bethe ansatz and quantum spectral curve. In AdS5 S5, this has been a derivation through Y system, T correlation. It is a non-trivial derivation to connect these two. But in principle, you can also bootstrap some quantum spectral curve, and from the proposal of the quantum spectral curve, try to take some large volume limit. And as a consistency check that the equations are correct, these people in particular, the last paper comes from Kamar, Gromov, and Stefanski, re-derived what are the dressing factor of S matrix. So this is a kind of consistency check that everything should work fine. But what I would like to speak about today is the case in which both H and K are non-equal to 0, okay? So in principle, you have some worksheet S matrix, which is known by imposing that it should commute with the supercharges of your theory. What it is not known is an overall multiplicative factor in front of S matrix. So any scalar factor that you put in front of S matrix, of course, does not modify the commutation relation. And this additional factor is something we need to check and we need to fix by requiring additional properties. For example, unitarity, crossing, fusion, and dates back to Zamologikov and Zamologikov, in which you should use the bootstrap method to fix what is this basically factor. Okay? So a proposal for this, at least part of the solution for this dressing factor, comes also in this paper by Olson, Sak, Ryabichenko, and Stefanski. What I will try to tell you is the part which is missing basically in this paper. So there is a proposal which fixes part of this factor. What is not fixed is the part which involves the BS phase, and this is what I want to talk about mainly today. So the plan is mainly looking at the massive part of S matrix, and in this case, I will look at the crossing equation in the case in which you have K equal to 0, so just Ramon, and then I will look at the case in which K is different from 0, and you have indeed this mixed flux. I will also mention about massless particles, but since I don't have much time, I think that the massive case anyway contains more or less all the information of your theory, and you can generate then the massless matrices as a particular limit of a massive one. So I'm happy to discuss more if someone wants to chat about the massless S matrices, but in this talk I will mainly focus on the massive ones, okay? So what are the massive particles of my model? They live in short representation of this gauge-fixed supersymmetry algebra. There are some left particles, this is a left representation, and in the dispersion relation, we connect the energy as a function of a momentum. P is my worksheet momentum. They appear the amount of NS and S flux, so this K, which is a quantized number, and this H, which is the amount of Ramon fluxes. In the other one, in the other representation involving right particle, and somehow these particles are the charge conjugate of these ones. So if you have Y, which belongs to some left representation, then you will have some Y bar belonging to the right representation, okay? Each particle here contains an antiparticle in the other representation, and particle and antiparticle are connected by the fact that on one side, this K, the amount of NS and S flux, comes with the plus sign, on the other side comes with the minus sign. So swapping the sign of this NS and S flux connect particles with antiparticles. So what I want to fix are these dressing factors. So I should say that within this multiplet, you can scatter. The theory is integrable. So you can have a mixing between left and right particles or mixing within the same multiplet. But at the level of representation, the scattering is purely elastic. So if you start with two left particles, they scatter to each other, but remains in the same representation, left. So in principle, you have 4 different dressing phases, which are not fixed by symmetry, corresponding to the scattering of left, 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 right, right, left, and right, right. Okay, and this is what I want to fix, and I'll try to fix in this talk. And the idea is that we want to fix an S matrix both in the string and in the mirror region. So how does it work in AdS5? AdS5, normally people work out this first in the string region, where tau and sigma are my worksheet coordinates. And after you find the S matrix in the string region, you would like to analytically continue to the mirror region, in which you do some double-wick rotation in such a way that after this double-wick rotation, you get some mirror theory, which in principle is different from the theory you started from. And the reason why we are interested in doing this is that in the mirror region, basically what Zamologic will teach us is that if you have some finite volume theory, this is equivalent to a theory in which the volume is infinite, but you have some finite temperature, which is exactly the inverse of the worksheet of a string. And this should keep into account of the wrapping correction and allow you to quantize the string. But the idea is that you want some S matrix, so this is a double-wick rotation, so energy and momentum on the string correspond to momentum and energy in the other theory. And if the theory is not relativistic, like in this case, you start with some dispersion relation, where you have some energy E connected to the momentum of the worksheet in this way. M is a bound state number, so M is equal to 1 for fundamental particle, that can be 2, 3, 4, 5, etc., etc. After you do this double-wick rotation, due to the fact that this dispersion relation has this form, you turn down in a dispersion relation which is non-real anymore. So on the right-hand side, you see if P tilde, which is the worksheet momentum in the mirror theory, say, is real, then the energy cannot be real too. So you start with a unitary theory, a well-defined S matrix, and you end up with a theory which is non-unitary in principle anymore. But still, if you have some string S matrix and you want to connect to some mirror S matrix, we believe that this can be done by some analytic continuation, and this is what actually we do. We derive some S matrix, and we are able to continue from one region to the other. And there are certain properties that must hold on both sides of this analytic continuation. For example, braiding unitarity. Okay, braiding unitarity is a relation which connects some S matrix at P1, P2 with another one at P2, P1. This is a relation which can be analytically continued. But for example, unitarity is not a relation which can be analytically continued everywhere. And indeed, on the mirror side, this property fails down. And similarly, if you have, in the mirror theory, parity is a property which is preserved, after you do this double-wick rotation, we should map to some time reversal symmetry. So the mirror theory, the string theory, sorry, is time reversal, but it's not anymore parity invariant. And these are all checks that should be done on all these properties that we know to be valid at the level of the Lagrangian when you do this double-wick rotation. So we would like to preserve at the level of the S matrix too, okay? So let me just discuss what it is crossing. So crossing is one of these properties that I listed here that must hold on both sides of the correspondence, and I say it later because I want to discuss now about the crossing equation. And the idea is that if you have a pure Ramon background, so this is most similar to AdS5 S5, you need to solve some inverse of this Zukowski map. And I will try to solve the theory, by the way, on the mirror theory side, instead of a string theory side, and eventually analytically continue back to string theory afterward. So you can do this on both sides of this correspondence. And there are two solutions to this equation. One solution contains the imaginary part of x, which is less than 0, and the other solution contains the imaginary part of x, which is bigger than 0. Of course, if x solves this equation, 1 over x also solves the same equation. And in principle, if you look at how it is done, the u-plane, you have some u-plane with long cap between minus infinity and minus 2 and plus 2 plus infinity. And doing a crossing transformation corresponds to start with some u, you cross one of this cut and end up with the same point u. And under this transformation, x tilde of u, which originally is below, is on the negative side of the complex plane, comes above and becomes 1 over x tilde of u. This is what happens in the Ramon case. And under this transformation, if you look at how the energy and momentum are parameterized in terms of these Zukowski variables, where I label x tilde plus minus in this way, where h is my amount of Ramon flux, you have that under this crossing transformation, energy and momentum change sign, okay? So what happened? If I look at the S matrix, I normalize the S matrix in this particular way. As I was saying before, there are 4 possible representations of your theory, which are 4 possible dressing phases, right, right, left, right, right, left, and left, left. Here I normalize the scattering of 2 right particles, Z bar, and the scattering of a left and a right particle, Y and Z bar, okay? And the reason why I don't look at the other 2 is because they are connected by left-right symmetry. As I was saying before, in principle, when you swap the sign of k to minus k, you should map Z bar, which is the scattering between right particle, to the scattering of 2 Z particles. And in the Ramon case, since k is equal to 0, these 2 are exactly equal to each other, okay? I put this prefactor here, which should take into account the fact that Z bar should form bound state. So this is just something that I introduce in my normalization in such a way to have the correct pole structure into the S matrix. And these 2 free functions are my dressing phases, okay? Everything I'm doing has already been done for Ramon, so here I'm just fixing some normalization, which is there also in the Ramon, okay? This is a Ramon in the mirror region. What are the crossing equations then? The crossing equation takes this particular form. So there is a red part, which is called odd part of the crossing equation. The reason why it is called odd part is because if you cross 2 times the left-hand side, this part changes, while this blue part does not change. It is called even part. And somehow this even part is an artifact of the fact that I put exactly this factor here. If I would have not put any pole in my normalization, then you just don't have this part. So somehow it seems trivial. But we also know that this even part is what contains somehow the interesting dynamics of the theory. And the BS dressing factors should be something that generates this particular part of the crossing equation. So I split the solution into some red term, which solve the odd part of the crossing. And this was shown, for example, in the paper by Alessandro Sfondrini and Sergei Frolov to be written, that can be written the solution in terms of particular gamma variable, which are originally introduced by Torrielli and Andrea Fontanella, I think. And this even part of the crossing equation is solved instead by some ratio of BS and Hernandez-Lopez. So what is the minimal solution for the odd crossing equation? As I was saying before, you introduce some gamma variable, which are connected to the Zukowski in this particular way. And then in terms of this gamma variable, you define some ratio of Barnes. So these are particular functions. Barnes gamma function can be written as infinity product of standard gamma. And even it may look quite ugly, the kernel is quite simple for these functions R. In particular, if you derive the log of R respect to Z, you obtain something like Z cotangent of Z. It's something very simple, the kernel. And this odd part of the crossing equation is solved in terms of this R function, whereby gamma tilde minus minus, I mean gamma tilde 1 minus minus gamma tilde 2 minus. I'm using this convention here, okay? So now let me go to the crossing for k different from 0, and I postpone the discussion of BS and Hernandez-Lopez to the k generic. In the case in which you have different k, by the way, I still have 15 minutes. 15 minutes, okay. In the case in which k is different from 0, I think this map anyway was introduced originally in this paper I'm not sure who was the first one introducing, by the function coherent cycling. You have two different Zukowski map. One is for the left particle, where k, the amount of an SNS, come with a minus sign, and one for right particle, in which this sign comes with a plus. And in this case, you have two different solutions, okay? You can have that if x left solve the first equation, the equation number A, 1 over x left solve equation number B, because under the inversion, the log change sign, and this is a trivial fact. So you have a different solution. One, the solution of equation number A, say, is x left and 1 over x right, and the solution of equation number B is x right and 1 over x left. So you need to keep a distinct label for left and right particle. And if in the case k equal to 0, after you cross this long cut, you end up in 1 over x. In this case, in which you have k different from 0, again, you cross this long cut, which is the analog of a cut plus 2 plus infinity, and from x left, you end up in 1 over x right. This is a bit of a message. So what we are doing, you start with some energy and some momentum of a left particle, and after doing a crossing transformation, you end up to having minus the momentum and minus the energy of a right particle. So this is the idea. So when you want to construct something which scatter trivially with all the state of your theory, you need to put together some particle, some antiparticle with opposite energy and opposite momentum. This transformation is what connects the energy of a momentum of some particle with the negative of a momentum of energy of an antiparticle. What I do now, I fix some S-matrix normalization exactly in the same way as I was fixing for the poor Ramon case. I just need to put some label. Okay? Before there are no label. Zukowski were all the same. Here I put a right and left in correspondence to the correct particle. If y is a left particle, means that I'm scattering x1 left, and z bar is a right particle, I scatter x2 right. And then again, I have exactly the same type of crossing equation. There is some odd part, which is a part which was solved by Bogdan and collaborators. And then there is this even part, which we solved by proposing a particular combination of BS and Hernandez-Lopez. So again, I split the solution into these two terms. How do I solve this odd part? The way in which we solve it, it is basically the same solution, but Stefanski and collaborator propose as an integral, while we propose as this particular combination of bars, but you can check numerically that they agree. And the idea is that you promote this gamma tilde variable, which originally has branch point at -1 and +1. And now, after you introduce k, these branch points move a little bit. So there is this parameter S, which is this particular combination. As you can see, if k becomes 0, this is exactly 1. But if k is different from 0, you have this different proposal for gamma left and gamma right. And then what you do, you take the solution for the Ramon case and just replace gamma 1. And this should have been a gamma 2, by the way, but okay, you substitute instead of gamma 1 and gamma 2, gamma right 1 and gamma right 2, depending on what dressing factor are you looking at. But it's basically some smooth formula in which you want to generalize to this case. While for the even solution that we solved in mirror theory, we use the Dory-Hoffman-Maldacena representation of improved BS dressing factors, in which basically the improved BS dressing factor can be written in terms of these building blocks as an integral in the x-plane, which runs over the real line. What is the real line is the boundary between what it was the mirror and anti-mirror region. Okay? So this representation in this way for the mirror theory, I think, was used for the first time by Gromov, Kazakov, Kozak, and Vieira. And what we want to do is to generalize this case to the mixed flux. Okay? So in this case, you have that case different from 0. So what happens? It happens that u, as a function of x, contain a log cut. So you need to decide if that representation runs as an integration path, which runs below the cut of the log or above the cut of the log. So you can have different combination of this phi function with different possibility for your boundary. And in this case, you need to put some label, A and B, which correspond to left and right and left particle, which enter these u's. As we were saying before, you left come with a plus k over h, and your right was entering with minus k over h. Okay? Sorry, it's the opposite, but anyway, there is a sign different between left and right. And then you need to decide your boundary. And I define this boundary to be plus of minus. Minus corresponds to run below the real line and plus above the real line. And it turned out that the only possibility to have a solution which is compatible both with crossing and with parity of a model is the case in which if you have two particles of the same time, they can be right or both left, you must have the same type of contour. So it can be minus minus or plus plus. And if you have particles of different types, like left right, you have opposite contour in the solution of the crossing equation. Of course, this in the limit in which k becomes 0 becomes the standard building block for the improved BS dressing factor, okay? And this turned out to agree also perturbatively. So if you take a large string tension and you take this particular combination, is something that reproduces exactly the FS order and the perturbative computation at 3 level at least. So the proposal for our k-deform improved BS dressing factor is this one, in which you take this building block, and then you have different phases depending if you scatter left, 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 right, and so on and so forth. And to read off the Hernandez-Lopez order of this phase, you take H to be much bigger than 1. And from the expansion, we have been able to read what was the first leading order, which is AFS, and Hernandez-Lopez. And if we replace inside our even dressing factor now this particular ratio, what we generated from our dressing phases, we have a solution which is compatible with crossing. We generate exactly this ratio of few terms. This, in principle, completes the proof of crossing. Of course, is not enough. Once you have some phase which solve the crossing equation, you can still have freedom to add the CDD factor, what are called CDD factors, so some function which satisfy homogeneous crossing equations and does not modify the solution. So we still need to check that all the other properties are satisfied. So now I come to the final part of the talk, which is indeed regarding the check and possible future directions. So what we have are analytic expression for this mixed flux S matrix which satisfy the symmetry requirement. And one property, for example, that we check is that this function has good periodicity properties for the different values of M. If you look at what is the dispersion relation of a right particle with arbitrary bound state number M, is this solution here. And you can see that has a certain periodicity. If you shift M by K and the momentum by minus 2 pi, you obtain the same type of dispersion relation. And this would be nice if also the S metric has some nice periodicity exactly in the same form of this dispersion relation. And this is what happens, actually. So if you shift the bound state number by K, is equivalent to shift the momentum by minus 2 pi. And somehow this S matrix, you don't have to study all the region of all momenta and all the bound state number, but it's just reasonable if you restrict to some bound state between, for example, 1 and K, because all the other bound states correspond to shifting this momentum here, okay? No, this is something, what we did was to check, for example, parity and char conjugation and parity. This is not something we should expect, but it would be nice if there is either a symmetry like this or some monodromy of the solution. So this is something, in principle, doesn't have to hold, at least for me. But if you have all the possible, and what happens? In Ramon cases, you restrict momentum between 0 and 2 pi, and you have all the bound state number. Normally, what happens is this. Here, you have all the momenta and all the M's. But it would be nice if you can restrict still between 0 and 2 pi and consider all the bound state number, or consider all the momenta, but restrict the bound state number between, say, 1 and k minus 1. So, and clearly, there must be something which reduces your space of possible parameters to a subset. Otherwise, it seems to be too much. And another limit that we consider, still 5 minutes, or a bit more, okay. Another limit that we consider, this was a paper in 2023, and a similar one came out before. Actually, a similar limit was considered by Fontanella and collaborator, is to study the energy as a function of the momentum, but instead of looking to all possible region of momenta, just to take H to be very small, and if H becomes very small, basically you have a singular as only one minimum. So this dispersion relation becomes something like, say, an angle. And you look around this minimum of this dispersion relation of fluctuation of order h. And if you do so, the theory becomes relativistic. And in particular, the spectrum of this theory contains a finite number of particles with masses which goes from 1 to k minus 1. And this is very similar to what are called a fine Toda theory of type A. Anyway, so there is a spectrum which is much restricted. And if you apply the bootstrap in this particular relativistic limit, what you obtain is that the relativistic S matrix contains some CDD factor and something which is the minimal solution to the crossing equation, where these are the same function I was introducing before. But before the limit, the solution is quite different, our proposal, because we have something which is u plus 2I over h and u minus 2I over h, which in the relativistic limit becomes some rational function of the rapidity, while by solving the bootstrap in the relativistic limit, we obtain some hyperbolic function of the rapidity. So the question is how this proposal can reproduce exactly this relativistic limit, and it does in a very non-trivial way. So what happens is that exactly this term reduces to a ratio of rapidities, but this even dressing factor produces exactly the inverse of this ratio of rapidity and also produces this ratio of Sinch. So this is quite nice result, I think, which I think is a good indication of the correctness of the proposal. So other thing we tested was a large tension limit, so what is called near BMN limit of the proposal, and we agree that 3-level matches perturbative computation at one loop in matches the cut constructable part of the S matrix, which can be found, for example, in the paper by Lorenzo Bianchi and Ben Hoare, but many other papers have been published, for example, by Linus Wolf and Arkady Young also. So it's still a mystery why we don't have a match for the non-cut constructable part. I think some of this computation would be interesting to review. But this is something which also in the Pura-Moramon case, there is no agreement as far as we know. And also from the proposal of the quantum spectral curve, there is no agreement about this part. And then the massless S matrix should correspond to a particular limit of a massive one in which u plus and u minus, your Zukowski variable, are very close to the cut. And in particular, you can have that they approach the cut either this long cut on the right or the long cut on the left. And we should generate two different branches of your kinematic which are not connected by analytic continuation. This is the picture in the U-plane. And taking m to 0 in our solution for a massive, apart from adding little CDDs, we reproduce what should be the massless case, okay? So let me just go to the future direction. What we have now are equations for the thermodynamic Betanzas which involve all the dressing factors. These still need a lot to be investigated. So we still don't have a clear perspective of what are, for example, the integration region in which you should integrate the TBA equation. So we have the kernels, but still is a mystery if you have a non-unitary theory, what does correspond to integrate, for example, on the real momentum region or on the cut in the U-plane. What is the correct prescription is still a mystery. So the hope is that even if a contour can be ugly, you can deform them and choose some nice contour. As soon as you don't cross, for example, any poles, you should be fine, but you need to do this very careful. So doing numeric in this model should be quite complicated. We hope to be able to do so at least in some region. For example, it would be very interesting in the case in which k is equal to 1, and you expand the small fluctuation of order h, because that should correspond to the formation of the orbital point, the symmetric orbital point. But we hope to return to some of these questions in the future. And of course, there are more general integrable backgrounds. For example, you can substitute T4 with S3 S1, and that talk was given yesterday by Niccolò Primi. This is also something that you can do in the mixed flux case. Even Ramon is very complicated, so I don't know how much you want to push up, but it would be interesting to see. So I just put some of the direction that we retain interesting, and I finish here. So if there are questions at this point, I will be happy to.
Thank you. Questions?
Thank you. So can you explain what simplifies when h goes to 0? Because you expect massive simplification. Do you see, because branch points don't collide like in the case of n equals 4. h equals 0. So
when h goes to 0, what simplifies?
Yeah. Like, I mean, in n equals 4, there is always simplification. X become u, right? Everything, no cuts. Life is beautiful. So what about here?
Yes. Okay, I wrote down what should be the cut structure in this case. You have these two cuts and this cut. I didn't write down the expression of this point here. When h goes to 0, what happens is that these two cuts becomes like this. They overlap one each other. I don't know how much simplification you have. A thing that happens, for example, if you consider k equal to 1 from this formula here, is that basically there is some kind of identification of your particle of your model. It's something like everything becomes massless. And every time you swap by, everything becomes massless because the massless mode m equals 0 and m equal k by this relation somehow are identified. So a particle of m equal k and m equal 0 are kind of very similar. If k is equal to 1, even the massive mode are equal to the massless one. So in this case, you can expect that there is something strange happening. I don't want to say nothing about the case in which h is 0 and it's true, it's a pure NSNS, so something nice should happen, but I think it's a strange limit from the point of view of S matrix because you have this long cut with overlap. And in this relativistic limit, it becomes some type of relativistic theory, but this is a particular relativistic limit in which also the momentum are expanded around some minimum. So don't know in general.
That's obviously very interesting to us with the BS phase. So what does it really do? If you think of some kind of small g expansion of the thing, so you cancel some terms and was it like a discontinuity? I mean, what's
Sorry, I didn't understand the question.
If I take your new phases
yes,
and do a small g expansion, so what would I see as a difference to BS?
Small g expansion? What do you mean? Sorry.
Like yeah, small h, shall we say?
Okay, small h expansion of a phase. I think it's the question of Collier.
Right.
So I still don't know. I should try. But, I mean, apart from this relativistic limit is similar to do that, right? Because you have that. I mean, h is small, but I'm also expanding like a small momentum around my solution, and in this case, the theory becomes relativistic theory composed of massive particles. The question if you also go away from this point is something which should be investigated. For example, I know Alessandro Sondini, together with Andrea Day, did a proposal for the pure NSNS case in which they proposed some S matrix which now I think they consider to be one in the same collinear, in the case in which the momentum were collinear, and they managed to reproduce the same spectrum of this Verzomino-Witten model. But that is not a smooth limit, so who be interested to revisit this limit having the correct S matrix? Because it's strange that that limit is not completely smooth, so it's still curious how they managed to reproduce the spectrum. And we expect to reproduce the spectrum as a limit of the total S matrix, I think.
Okay, thanks.
I don't see any more questions. Maybe I would ask a question. Some people raised this question, including me. What would be a fishnet type limit here in this model? You don't have any idea?
No, I don't have any idea.
Let me maybe give some hint. If you can show me...
yes.
if you can show me the dispersion relation, like with...
Yeah, let me see. Okay, this is for right particle and for left here.
Yes, this one. So in our paper with Omer and João Caetano, we observed actually this limit already on this level. Like you send h to 0, p to I infinity, and then instead of this first term, we had 1, and then it nicely scales into some dispersion relation with twist, yes, like spin chain with twist. Here, it's natural to maybe to send, if it's not crazy, it doesn't look crazy to you, m to I infinity, p to I infinity, yes, and then you can balance two terms. And I think in our case, the the S matrix truncated to something like the homologic of ON. So maybe it could be done
Okay.
this way here.
We can discuss it.
Interesting to see.
Yeah.
Okay,
Thank
you. If there are no more questions or proposals, let's thank the speaker again. I don't know.
Yeah, let's see. Hello, hello, can you hear me?
Yeah.
Okay. I didn't need to point at that. Yeah, that's right. Okay, good. Thanks.